Okay, good morning, ladies and gentlemen. Welcome to 15-51, Great Theoretical Ideas in Computer Science. So I've heard that it's been also described as the death course. I guess it's because you'll have so much fun in this course, you'll die from overjoy. Right? That's the real reason. Okay, so these lectures are being recorded. So if you don't want the back of your head to be in the video, I guess you have to sit on the sides or at the back. So just keep that in mind. Another thing is, we would really like if you didn't use your electronic devices during the lectures. But if you really have to use them, then maybe you can sit at the back because it's really distracting to the people around you. Okay, so with those out of the way, I guess I should first introduce myself. So my name is Anil. You can call me Anil. I'm one of the instructors for the course. Professor Ryan O'Donnell is back there. He's the other instructor of the course. He's pretty awesome. We're lucky to have him. Then I think we also have a couple of TAs back there, but they're not important. No, I'm kidding. So Thompson is there, yeah. And then Chris, I see Chris. I guess those are the two for now. You'll get to meet them on Wednesday night, but I'll say more about that later. So anyway, so let's start with the basic question, right? So this is a course on great theoretical ideas in computer science. So the most basic question you can ask, I guess, is what is theoretical computer science, right? And I guess we can even start with the question, what is computer science? Okay, so I'm actually interested to learn about your ideas on this. So who would like to volunteer their idea on what computer science is about? Just not theoretical computer science, but just computer science. What is computer science about? Anyone? No one. Most of you are computer science majors, by the way, right? Yes? Using computers to solve our everyday problems. That's good. That's very good. Anyone else? Yeah?
Study of computation.
Study of computation. I like that. Okay. All right. So then, okay, what is then theoretical computer science? What does theoretical add to that? Or what do you think of when you hear the word theoretical?
Studying what could be accomplished with technology that might not exist yet, but could theoretically exist, like not limited by current implementations.
Not limited by current implementations, but what theoretically could exist, what could be possible. That's interesting. That's nice. So I was talking about with my friends about this. They were asking what I do, and I tell them I'm a theoretical computer scientist. And apparently, what they think of when we say theory is like philosophy. Like theoretical computer science is somehow the philosophy of computer science, which I thought was interesting. So, well, obviously I'm biased, and I know what theoretical computer science is, but the first thing that comes to my mind is math, actually. And we'll see why. So if we were to ask the layperson, here's the layperson, I think what the layperson would say about computer science is writing computer programs that do certain tasks, right? Seems reasonable. So what we're going to try to do in this lecture, and I guess throughout the course, is prove that this guy is wrong, or to show that computer science is much more than this. Okay? So what is computer science? Is it a branch of science, like a natural science? No? Okay, we'll see. Is it a branch of engineering? Is it a branch of mathematics? Yes, okay. Is it a branch of philosophy? No? Is it a branch of sports? Well, you know, if chess is a sport, then maybe computer science is also a sport. Okay, so to understand these things, what I'm going to try to do first is draw an analogy between physics and computer science, and the role of theoretical physics within physics, and the role of theoretical computer science within computer science. Okay, so let's look at physics. So you could say, perhaps, that physics, you can maybe divide it into three main parts and say, well, there's theoretical physics, there's experimental physics, and maybe there's the application stuff. Okay? Now, what does a theoretical physicist do? So you observe some phenomenon occurring in the universe, right? So maybe you observe it yourself, or maybe your experimental physicist tells you, look, I've observed these results. And then the theoretical physicist, what he or she will try to do is come up with a mathematical model that, models that phenomenon. Okay? And that's interesting. You might ask, why a mathematical model? And, it turns out to be the case that nature's language is mathematics. Okay? So this is quite interesting. It didn't have to be that way. I mean, this is the relationship between physics and mathematics is really, I think, mysterious. No one really knows why the language is mathematics. But it is the way it is, and it's pretty cool. We like it. And then what you can do is, once you have that mathematical model, you can derive all the logical consequences of that model and see what else you get. Okay? Now then, the experimental physicist will make observations about the universe, of course, and also make direct tests about the model that the theoretical physicist came up with, and see if it agrees with experiment or not. And if it doesn't, well, the model is wrong, right? We have to change the model. And then we have application. So we have all this, we're studying mathematically all this natural phenomenon, and then we can ask, can we now apply it to in a useful way to our real world? Okay, so if we looked at the role of theoretical physics within physics, we might maybe draw a picture like this. We might say, okay, we have the real world, we observe some phenomenon, and then we go to the abstract world, we go to the mathematical world, and we have our mathematical model. Okay, and then we live the theoretical physicist sort of lives in that abstract world, explores all the consequences of these things, the mathematical model, and then first thing you can do is test those consequences and see if the model is good or not. But also you can look at some applications of these consequences of your model and go to the real world, back to the real world like that. Okay? So theoretical physics, is it related to natural science? Is it a natural science? For sure, right? Because it studies natural phenomenon, tries to understand it. Is it like engineering? Is it related to engineering? I think, yeah, it is related to engineering as well, because you also want to see if your model has applications in the real world. It's related to math, for sure, because we live in the math. That's the language we use. We live in the math world, the abstract world. Is it related to philosophy? Yeah, I think so. Well, I mean, the deepest questions that we might ask, like whether the universe can come from nothing or whether something can come from nothing, those are philosophical in some sense questions, but also questions that physicists would like to tackle. Is it sports? Well, I don't know. So now let's look at computer science, okay? And let's see if we can see an analogy there. All right, so computer science, if I wanted to define it or explain it using as few words as possible, I don't know why I would restrict myself to do that, but let's say I do. Then I would say it's the science that studies computation. Okay? But of course I'm cheating here, right? Because I didn't define computation. Okay. Well, what is computation? If I wanted to use the broadest possible definition, it's the manipulation of information or data. Okay, that's the broadest possible way you can define it, and I think it's a useful way to look at computation in this way. It's an interesting way to look at it. And usually, what we have is we have some input data, so then there's some computation going on, and it produces this orange thing, whatever it is, some device, will produce some output data. Okay, so that's usually what happens. And let me add a couple more keywords here. So another keyword that you will use and often hear is like algorithm. What's an algorithm? Well, in this context, the algorithm is the description, a precise description of how the data is manipulated. Okay? And maybe another keyword here, computational problem, we can say is the input-output pairs, the collection of input-output pairs here. Right? It's a thing that is being computed by this orange thing. Okay, so computation, at first, this definition might be a little vague, but maybe think about calculation, right? So you're maybe more familiar with the concept of calculation. What is calculation? It's just the manipulation of numbers. So it's a restricted form of computation. So computation is more general than calculation. It's manipulation of not just numbers, but also other kinds of data. Okay? So, examples. A calculator does computation, right? So you give it some numbers. It can do multiplication, division, addition, subtraction, whatever. So certainly a calculator does computation. Certainly your laptop does computation, no doubt. Now let's look at some other interesting examples. How about people, humans, or other kinds of animals? Right? So we do computation, right? So we get input from through our 5 senses. Our brains process that information and then produce output, usually in the form of muscle movements. Cool. Let's go further. How about evolution? Can we view evolution as computation? So I think we can. Like, our definition is general enough that we can definitely say, we can definitely view evolution as computation as well. Right? So this is why computer science is really interesting, because you can view natural processes as information processes. And in some sense, computer science is the science that studies those information processes. Now, I should say, like, this the computational perspective, let's say, on evolution. Is it useful or not, is another question entirely. Okay, so it might be the case that you can pretty much view any natural process as computation, but it may not be a useful perspective. So whether it's useful or not is another thing. In the case of evolution, I think it would be a useful perspective. But the point here is that you can view these natural processes as computation. Okay? So you can indeed apply the computational lens to various fields and get like computational physics, computational biology, computational chemistry, computational neuroscience, computational finance, and so on. Right? And sometimes the computational lens is very useful. Sometimes it may not be very useful. But it's interesting nevertheless. And as I said, this is one of the reasons why I think computer science is very interesting. Sometimes students will come to me and ask, should I choose computer science as my major? And I tell them, yes, you should. Because you may not like everything about computer science, but certainly you should find something within computer science that interests you, I think. For example, I personally don't care too much about computer programming, but I love computer science. So you might say, what? That doesn't make sense. But I mean, it's true, right? So computer science is much more than programming. And I guess the purpose of this course is to illustrate that point. But yeah, I love computer science because I love the theoretical foundations and the theoretical study of computer science. Okay, so if you don't believe my definition of computer science, well then let's look at Wikipedia, right? Okay, so Wikipedia says that computer science deals with the theoretical foundations of information and computation together with practical techniques for the implementation and application of the foundations, which is, I think, a very good definition. I was surprised when I saw this. I didn't expect it from Wikipedia, but it's very good. Okay, so then what is the role of theoretical computer science? Again, within computer science, well, the first thing we have to do, of course, is what? We'll build the mathematical model for computation, right? Just like a theoretical physicist builds a mathematical model for the universe. Right? So we build the mathematical model for computation, we explore all the logical consequences, and we gain deep insights about computation, and try to understand it better, and then we also would look at some interesting applications back in the real world. Okay? So here's the picture. We have the real world computation. We observe computation in the real world. We go to the abstract world, we have the mathematical model, we explore the consequences, we live in that abstract world, and we also look at applications in the real world if there are any. Okay, so in this sense, it's like very similar to theoretical physics, right? So theoretical physics explores, you know, arbitrary phenomenon that occur in the universe, and you can think of computer science as like studying one aspect of that universe, and that aspect is information processing or information manipulation. And that is a very important aspect. Now what's interesting is that you might know that computer science is a relatively new field, right? So maybe not even 100 years old, right? So that's interesting because the concept of computation is very fundamental concept. We've been using it for thousands of years. So how come computer science is such a new area? Okay? And the reason really is that this formalization going from computation in the real world to this mathematical model of computation was only done very, very recently. Okay, so like in the 1930s and 40s. Okay, so let me tell you, I'm going to tell you a little bit about that now. But first, let me make again the point that we've been using computation, we've been using algorithms for thousands of years. So here's a very simple algorithm for multiplying two numbers. I don't know the origins of this, but I'm guessing this has been around for thousands of years. Here is Euclid's greatest common divisor algorithm from about 300 BC. So, you know, we've been coming up with algorithms. We've been, you know, thinking about computation for many, many years, but we haven't formalized the notion of algorithm computation until recently. It was only done in the 20th century. Okay, and experience shows that, you know, if you want to really understand something deeply, it's a good idea to formalize it mathematically and study it that way. Okay. Now, why it wasn't formalized until the 20th century is probably because someone had to ask the right question for it to be formalized. And I'll tell you about the little history behind this. And I think it's a really nice little story because it shows you, like, if you want to make great contributions in the world, you don't always have to solve a major, you know, existing open problem. Sometimes it's enough to just ask the right question. Okay? So the person who asked the right question was David Hilbert. Okay? So this is now, we're going to 1900. So David Hilbert was one of the most famous mathematicians at the time, maybe the most famous, arguably. And in 1900, he organized a conference where he gathered together all the greatest mathematicians of the time. And he gave a talk called Problems of Mathematics. He presented 23 math problems that he thought was the most important and challenging mathematical problems of the time. And he started his talk by saying the following. Okay, so let's read this. Who among us would not be happy to lift the veil behind which is hidden the future, to gaze at the coming developments of our science and at the secrets of its development in the centuries to come? What will be the ends towards which the spirit of future generations of mathematicians will tend? What methods, what new facts will the new century reveal in the vast and rich field of mathematical thought? Okay, so he was a very inspirational guy, and all the mathematicians were pumped up after hearing this. They were ready to rock and roll. And then Hilbert's 10th problem was a special problem for us, for computer science. So Hilbert's 10th problem was the following. Is there a finite procedure to determine if a given multivariate polynomial with integral coefficients has an integral solution? Okay? Now, the exact problem is not that important. If you don't understand it, it's okay. The key thing here is that he was asking for a finite array procedure. Okay? So what is that? Well, he was asking for an algorithm. Okay? But I guess the technical term was not there yet, so he was just describing it as a finite array procedure. He didn't use the term algorithm. Okay, so that was an interesting question. And then later in 1928, he updated, he added some more problems. So this one is called Entscheidungsproblem, and I'm probably butchering how I say that, but you know, it's German, so that's in 1928. And this asked a similar question, similar in nature. It says, is there a finite array procedure to determine the validity of a given logical expression? So again, he's asking for an algorithm. And a given logical expression could be like, let's say, example, there is this not x, y, z, n in natural numbers such that n is more than or equal to 3 and x to the n plus y to the n equals z to the n. Okay, so people might recognize this as what? Who knows what this is? Fermat's last theorem, right? So this is one logical expression that describes Fermat's last theorem, but we can describe other mathematical statements using logical expressions. So basically what Hilbert was asking was the mechanization of mathematics, right? He wanted to know if he could get rid of all these mathematicians and do math just by using basically computers or, well, at the time there were no computers, but like just by a mechanical procedure, okay? Not involving any real human thought. Okay? Now, lucky for us, the good thing was that the answer to this question is no. Okay? So that was a great thing that it turned out to be no. Not just for the mathematicians, but for computer scientists as well. Because, you see, if the answer was yes, then, okay, all we had to do was come up with this procedure, finite array procedure, this algorithm that will do the task, and then we would present that algorithm, and we would be fine, and we would continue our lives. But the answer was no. Now, how are you going to show that you cannot have a finite array procedure for this task? Okay? you want to prove that, right? You want to rigorously prove that there is no finite rate procedure. Well, if you want to be able to do that, the first thing you have to do is define what do you mean by finite rate procedure, right? So this question basically led Church and Turing, right there, to first define what a finite rate procedure means, basically defining what computation is, and then show that, after that, you know, Hilbert's problem, the answer to Hilbert's problem is no, that there is no algorithm or finite rate procedure. And it led Turing to define in 1936 what we now call a Turing machine. Okay? And this was huge. Okay? This was one of the most important results in the 20th century. So a Turing machine looks something like that. We will learn about it in this course. It's not important, the details, but this was a huge step because this was basically the formalization of computation, the mathematical model for computation, and now we can mathematically study and understand this notion of computation, this important notion. And the other nice thing that happened at this time is basically the observation that we can actually have universal Turing machines. So what's a universal machine? So you see there's a difference between your calculator and your laptop. Okay, so your calculator can do some simple tasks like multiplication, division, and so on, but it cannot do any kind of computation, right? So it cannot basically, for instance, factor some integer. It cannot tell you whether an integer is prime or not, or it doesn't let you play Angry Birds. But your laptop is not like that. So your laptop, you can program your laptop to carry out any kind of computation you want. Okay? You can program a calculator and it will do what a calculator does. You can program Angry Birds and you can play Angry Birds. You can do basically any kind of computation on your laptop, and that's why it's called a universal machine. And so really this concept of a universal Turing machine, which we're going to learn in this course, is the mathematical model basically for the laptops and your computers that you use today. Okay, so this idea of a computer, the idea of a laptop, you know, it didn't come out of thin air, right? So first we had this mathematical idea, this mathematical notion of this universal machine, and then from that we overcame the engineering difficulties and we built these machines. So that was pretty cool. And now you can ask, of course, okay, we have this Turing machine as a model of computation. Is it the right model? Is it the correct model for computation? And we think, we strongly believe that it is the right model. And we captured that basically belief with this statement or thesis, the Church-Turing thesis, which says, sort of informally, I guess, the intuitive notion of computable is captured by functions computable by a Turing machine. Which is sort of vague because, what does intuitive notion mean? So I prefer actually the following version of the Church-Turing thesis. So there are various versions of this. It is sometimes called the physical Church-Turing thesis. And it says that any computational problem that can be solved by any kind of physical device, okay, any kind of physical device that you can come up with in this universe, can be solved actually by a Turing machine. Okay, so I like this because this is a more precise statement and it's rooted in physical reality. Okay, and you can think of this now Church-Turing thesis as the bridge between the real world and the abstract world, right? So this takes us from the real world to the abstract world, and then it's nice because now we can live in the abstract world where everything makes sense, everything is rigorous. It's not like your opinion against my opinion. Something is either true or something is false, and we can prove these things. Okay, so theoretical computer science, then, is it related to natural science? So I think it is, because it studies naturally occurring phenomenon, information processing. Is the part of engineering? I think it is, because you certainly explore the applications of your theoretical ideas as well to the real world. Is it a part of math? Certainly is, right? So that's the language we use. And in fact, if you look at the Clay Institute's mathematical Millennium Prize problems, the 7 most important mathematical problems of our time, each one having $1 million price tag, one of them is precisely a computer science question, which I'm sure most of you have heard, the P versus NP question, right? And you might, so by the way, one of those questions is solved, and the other 6 remain open. The person who solved, Perelman, who solved the Poincaré conjecture, if you don't know, it's an interesting story. He refused to take the $1 million. He was also awarded the Fields Medal, and he refused that too. And he said, I prefer to live with my mother instead. I don't want your money. Okay, so yeah, you should read more about that. It's pretty interesting. But one might say, the P versus NP question, which is one of those questions, maybe perhaps is the most important question among all those questions. Why? Because you can say, well, so the P versus NP question is a question about 2 sets, P and NP, and it asks whether these 2 sets are the same or not. Now, it turns out that if P is equal to NP and these sets are the same, then that means that I can actually solve the other mathematical problems. I can write a computer program to solve all the other mathematical problems. Why? Because proving mathematical theorems is actually a computational problem, right? So I can solve all these other problems, and then I'll collect my $6 million and then retire happily. So it's interesting in that way. But I guess I should also mention that most people believe that P is different from NP, and that's not going to be the case. But I'm not one of those people. All right. So is it related to philosophy? Well, I think it is. It is related to some of the deep questions that we can ask about, for example, intelligence. What does it mean to be intelligent? When can we say that a computer is intelligent? We talked about Alan Turing, so there's a movie out right now, The Imitation Game, so you should all go see that movie. Historically, it's not 100% accurate, but it's still a pretty good movie. So Alan Turing is, of course, for obvious reasons, is considered to be the father of computer science, but he's also considered to be the father of artificial intelligence, because he was interested in these kinds of questions of what does it mean to be intelligent? How can we determine if a machine is intelligent or not? And the name of the movie, Imitation Game, actually comes from that. So Imitation Game is a game that Alan Turing proposed to determine whether a machine is intelligent or not. Okay, so go see the movie if you haven't, and it's quite interesting. So it's, I think, in that sense also very much related to philosophy and maybe also sports. Okay, now there are various interesting questions in theoretical computer science. But I would like to focus on 2 main questions right now. Okay, so the 2 main questions in theoretical computer science are the following. So the first thing you can ask, the most basic question you can ask about computation is whether some problem is computable or not. Okay, so the most basic question you can ask, is every problem computable or not? Or are there problems that are not computable? And I guess most of you already know that the answer to this question, like whether every problem is computable, is no, right? So it turns out that there are some problems that are not computable. And if this is the first time you're hearing that, that might be maybe surprising. Because you might think, well, I'll just try every kind of possibility and eventually I'll figure out the answer. Well, no, it doesn't work that way. Okay, so there are some problems that are not computable. However, it turns out that most problems that are interesting to us are computable. So then, what is the next sort of question that you can ask? And the next question you can ask is, you're right, complexity of a problem, the computational complexity of a problem. And I like to, so this is like, is there an efficient algorithm to solve it? And I like to sometimes think of this as practical computability. Okay? Why? Because if you have a problem and the solution to the problem is going to take you a gazillion years to solve, well, okay, theoretically it is computable, but practically, really, it's not computable. Okay, and that's a very interesting question. So is there an efficient algorithm to solve it? And efficiency, of course, can be with respect to various different resources. The most obvious one being time, how much time it takes. Another one is space, or the amount of memory that you use. Randomness, so we can have randomized algorithms, we can do randomized computation, and we can ask how much randomness we're using. And if you want to be a bit more advanced, you can even look at quantum resources and ask how much quantum resources you might need to solve a problem. Okay, and within this area, I guess you can call computational complexity, there are mostly basically two camps. There are the algorithm designers who would like to try to come up with efficient algorithms to problems. Okay, they want to show that if you have this particular problem, I can do it using this much resources. Okay, and here is my algorithm to do that. And sometimes these are also called upper bound results. You're upper bounding the amount of resources needed to solve that problem. And then, from the opposite end, at the opposite end, we have complexity theorists who trying to show the sort of the opposite and show that no efficient algorithm exists for a certain problem, or that you need at least X many resources, X much time, or X much space to solve a certain problem, and these are often called lower bound results. Right? You're lower bounding the amount of resources needed to solve these questions, and if the lower bound matches the upper bound, then ding, 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 we're done. Right? So that's the goal. Okay, so there are, of course, many thousands and thousands of interesting, useful computational problems to study, ranging from engineering to medicine and sciences. Okay, but let me give you, anyways, a few of them here. So, for example, we can talk about matrix multiplication and say, can we improve the fastest algorithm for matrix multiplication? It's such a fundamental problem that so many algorithms use matrix multiplication that it's important to try to understand and improve the best bounds on that. Stock trading, maybe if you want to get rich. Protein structure prediction, a very important problem in biology, which would have enormous applications in medicine. Simulation of quantum systems would have enormous applications in nanotechnology and pharmaceuticals and various other things. Integer factorization. interesting problem as well. So matrix multiplication, stock trading, protein structure prediction, simulation of quantum systems. Obviously, like if you come up with good upper bounds on these, good algorithms on these, it has obviously interesting applications in the real world that would be useful. Now you might say, is there any application of showing that a problem is hard? Can we make also use of the fact that a problem is hard? And integer factorization is like a very good example of that, right? So it turns out that the cryptographic systems that we use, most of the cryptographic systems that we use today on the internet, for example, the security of those systems rely on the fact, the assumption, relies on the assumption that the integer factorization problem is actually a computationally hard problem. Okay? So every time you are shopping online, you are in a sense betting that the integer factorization problem is a hard problem. Okay? Another way to say that is, if someone had an efficient algorithm to solve the integer factorization problem, they could break all these cryptographic systems used on the internet today. Now, do we know integer factorization is hard? Actually, we don't. We haven't proven that. Okay, it's an unproven thing. So most people believe that it is hard, but maybe it's not hard. So that's interesting. Now, what you can ask, why haven't we proven this thing? It's such an important thing. Why haven't we proven that? Well, you see, algorithm design is sort of, if you want to be an algorithm designer, you design an algorithm, you come up with an upper bound. It's fine, but trying to show that no efficient algorithm exists is a different kind of beast, right? So how do you show that no algorithm exists? You have to argue against all possible ways of solving a certain problem. And that turns out to be a very big challenge that we actually really don't know how to approach. Okay, and here are some other interesting questions within theoretical computer science, and there are many others. So, for example, what is the relationship between space and time within complexity? So, if a problem, for example, has space-efficient solution, does it also have a time-efficient solution? Can every randomized algorithm be de-randomized efficiently? Okay, so do we really need randomness to speed up computation, or is it unnecessary, actually? So what's the role of randomness in computation? Can we use quantum properties of matter to build faster computers? Quantum computation, something that we'll also discuss in this course. So these questions and sort of other questions, there are many other interesting questions, are are at the heart of theoretical computer science. Unfortunately, with most of these questions, we're not even close to answering them. So maybe it's a good thing for you guys, so you can go into this field and try to tackle these questions. But yeah, as I said, the problem is like showing lower bounds, showing that something is not possible, showing that a Turing machine cannot do a certain thing efficiently. Turns out to be a considerable challenge. And in many of these problems, you need to show lower bounds. So that said, we do have very interesting results as well, and we'll see those interesting results. All right, so that's basically a little introduction to theoretical computer science and what theoretical computer science is about. Now, let me just say a few words about what you will learn in this course. So I've been telling you basically what the kind of things you will learn in this course already. But if I wanted to make a list about it, I could maybe list the goals as follows. I could say, number one, obviously, learn about the theoretical foundations of computation. So the things that we've been talking about. Two, we have to learn the basic math topics that we need in order to understand the theoretical foundations of computation, right? So we need to learn this language that we have to use. And that also means that we have to be better at reasoning abstractly and formally, right? Because that's what math is about. So we are going from this real world to the abstract world, and we're going to sort of live in that abstract world in the land of rigor, and become better problem solvers, I guess, right? So computer science is sort of about, problem solving, and hopefully you're going to be better problem solvers by the end of this course. And these skills, I think, are also useful in real life too, right? So I think it makes you a more rational human being, having these skills. And that's, I think, is a good thing. All right, so let's now take maybe a little break and watch this video.
Hi, my name's Sarah Borna, and I'm a math major. It's true, I'm a math major. I study math on purpose. And what I really want to talk to you about today is the kind of reaction I get when I tell people I'm a math major. And I say, oh, I study math, I'm a math major. And I usually get responses like this. Oh, my brain's just not built for that. I'm more creative. Oh, wow. Genius. I'm just too slow at it, I just can't, I'm just too slow. I just never really, it's genetic. Oh, I'm just not a number person. I hate math. Okay, so here's the deal. Math is hard. It is. We all know this. It's not like we go around speaking math all day and then can just switch in and out of it all the time. No. We have to stop and switch gears and change what we're doing, and that can be really confusing. It's as if we were having a wonderful conversation and then all of a sudden I stopped and asked you to write me a poem in Russian, and you don't know Russian, and so you have to stop and learn some basic Russian and then try to figure out what kind of poem I want. And maybe I'm helping you out, maybe I'm trying to explain what's going on, but there are some Russian words that don't really translate into English very well. That's really hard. And math can kind of feel like that when you're not used to it. In fact, math can kind of feel like that even when you are used to it. So nobody's expecting you to come into this world with every mathematical tool ever known to man fully formed in your brain. That's just not going to happen. So give yourself a little slack, No one's going to expect the right answers all the time. Okay, you know that kid in your class who just knows all the answers and is always raising their hand really fast and just makes everyone feel kind of stupid, right? Okay, let's go back to the Russian poetry analogy. Imagine you're in a Russian poetry class and there's a kid in the class whose family speaks Russian. Or maybe they speak, Ukrainian or something, and that's really similar, so he has a leg up. Or maybe, she listens to a lot of Russian music and just really likes it, and so she's picked up a lot of stuff. Stop comparing yourself to that person. Seriously, stop. You have no idea what a student's background is. Just because they can answer something faster than you can does not mean that they are better than you. And it does not mean that you are stupid or that you don't know how to do whatever skill it is. It means that they're in a different place than you. That's really all it is. Math is a skill. Did you know that math a week ago? Do you know that math now? Do you at least know some of that math now? is like a big victory at that point. It's just like learning how to sing or dance or ride a bike or cook or something. You might make mistakes. You might find it's really hard. You might, I don't know, fall off the bike. But that doesn't mean that you will never learn how to do those things. It means that right now you need more practice. So practice. You know, ask for help, demand help. Talk to people who seem to know a little bit more than you do. Maybe they'll be able to, you know, give you some advice. If that's too scary, talk to people that are on the same level as you and try to get a sense of what you don't know, and then go to your teacher. You can't practice if you're constantly talking yourself down. Math is hard, but you can do it. It's not magic. It's a skill.
Okay, so the land of rigor.
Mathematics. So obviously we're going to be writing proofs, right? When we do math, things are either true or false, and we want to know whether something is true or false for sure. So we have to prove these statements. Okay, so there are a couple of things, several things I want to say about proofs. First, I think writing proofs, finding proofs, is very similar to finding and writing algorithms. That's actually not very surprising because coming up with proofs is a computational problem. So it's sort of like a special case of finding and writing algorithms. But just like, you know, when you're first learning how to program, it can be sort of tricky at first, even to solve the most basic problems or writing the most basic programs. Similarly, writing proofs, even writing proofs for very basic things can be tricky at first. So it's a skill, right? It's a skill that is learned, and you have to practice until you learn, get better at the skill. And I guess like one tricky thing at the beginning when you're learning how to write proofs is like how much detail is good enough. So probably you're going to be in situations where like you'll be like, okay, I kind of see that this statement is true. Yeah, I can see that. But like now how do you actually write a formal proof for that? And how much detail is enough? Detail. Now, as you're learning to write proofs, I think it's good to err on the side of giving too much detail, okay, rather than giving not enough detail. So make sure that you're not, you know, making claims that are not obviously true. Okay? If it's obviously true, you're allowed to make that claim. But if something is not obviously true, that needs an argument. Okay? And another thing I want to say about writing proofs is that you know, there are no eureka moments when you're, you know, trying to come up with a proof to a statement. Okay? And let's look at one of the most famous, maybe the most famous mathematician that is living today, Terence Tao, who's a Fields medalist, MacArthur genius, and blah, blah, blah. So, you know, he's the most famous mathematician, probably like one of the smartest people alive in the world today. And let's see what he has to say about this. Okay? So I don't have any magical ability. When I was a kid, I had a romanticized notion of mathematics that hard problems were solved in eureka moments of inspiration. But with me, it's always, let's try this. That gets me part of the way, or that doesn't work. Now let's try this. Oh, there's a little shortcut here. You work on it long enough, and you happen to make progress towards a hard problem by a backdoor at some point. At the end, it's usually, oh, I've solved the problem. Okay? So, and this is really how you know, you come up with proofs, right? It's not like you start with 0%, you have no idea how to do it, and then bam, suddenly you solve the problem and you're finished. Okay, so it doesn't happen that way. So, you know, when you're working on some hard problem, some research problem, you can say, a good strategy would be to make 1% progress for 100 days, right? So, and then 100 days, hopefully you solved it. I guess in this course you don't have 100 days to solve a problem. So, for you guys, it's make 15% progress for 7 days. Okay? What else? So, give breaks, right? So don't like work on a problem for hours and hours and hours without giving break, like banging your head to the wall. Give yourself a break and let the unconscious part of your brain do some work, because it does, right? So when you're not working on a problem, it's actually your brain is still working on it, interestingly. And you'll realize that when you come back to a problem, suddenly things become clearer, magically, I find. Okay, so give breaks. That's I think, a good suggestion. Try to figure out some meaningful special cases that you can prove. Maybe n equals 1, n equals 2 if the problem is stated in that way. Find some meaningful subproblem that you can solve. Okay, and that can also like highlight where the difficulty in the question lies. If you can solve these sub questions, it can identify you, well, here's the problem, and it can also give you ideas about how to solve the general case. Put yourself in the mind of the adversary is always a good thing to do. What are the worst case examples or scenarios presented? You can think about those things. Develop good notation, use lots of paper, draw pictures. I mean, everyone is different, of course. Maybe you like to just have it all in your brain and not use any paper, but like, I think for most people, if you use paper and use visual aids, that's a good thing. And collaborate, right? So that's a very important part of doing research in these areas. And you'll also get a chance to collaborate with your friends and learn sort of how to collaborate as well. So now let's look at the course syllabus very quickly. So first of all, the course web page is right there. Pretty easy. I guess, let's see, if we go there, I don't know the current situation of the course web page, but let's see. Okay, there it is. So we have some basic information about the course. I don't know, the internet is not working. But, it looks something like that, basically. It's not, I believe it's not complete right now, but maybe check tonight. You should definitely read the course policy. It's very important. Actually, I think as a part of homework 1, we'll ask you to read the course policy written in there. Okay? Well, in the syllabus, of course, the most important thing is grading, right? That's the most important thing, so let's start there. So, homework. There will be about 11 homework assignments, basically once every week, more or less, and the lowest homework will be dropped. So this is going to be 33% of your overall grade. There will be 3 midterm exams. Lowest score will be half-weighted. So that means like the lowest one will be 7%. The other 2 are going to be 14% each, so in total 35%. And the midterm dates for now are scheduled to be on February 11, March 16, April 15, from 6:30 to 9:30 p.m. So you want to write those dates down and make sure that you are available during that time. All right, so we have, of course, one final exam. It's going to be 25% of the grade. There are going to be about 11 quizzes where the lowest score will be dropped. This will be just 5%. Okay, I'm gonna talk more about these things in a minute. And then there's also 2% participation grade, and this is basically to make sure that you're not a ghost in class. Okay, so I would definitely like to know all your names by the end of, I don't know, February 11, by first midterm. That would be nice. Okay. If I don't know your name, that's not a good thing. All right, so homeworks. Okay, so homeworks are without a doubt the most important part of this course. Okay, so this is where real learning happens. Okay, so sure, you're gonna learn during lectures. Sure, you're gonna learn during recitations, but really the learning is going to happen when you're struggling with the homework. And it's kind of like, you know, learning how to ride a bicycle. So if you watch someone ride a bicycle, or if you watch someone talk about riding a bicycle, that's not going to really teach you how to ride a bicycle. You have to do it yourself. And this is the idea here as well. And when you're first learning how to ride a bicycle, it's challenging, right? It's really challenging, but that's a good thing, because as you're challenged, you're actually learning. Okay, that means you're learning when you're challenged. So our homeworks are going to be challenging as well. Okay, they are meant to be challenging because, not because like we like to see you suffer and laugh at you. That's not the idea. So the idea is that we really believe that this is the way you learn things, by being challenged. Because that means that, you know, we're tapping into the regions of your brain that you have not used much, and, you know, we are strengthening the connections between these neurons, and you're literally getting smarter as you are struggling doing the homework. So I think like it's a good thing to change your perspective on this challenge and this struggle. So you want to embrace that challenge and embrace that struggle, because that's a good thing, not a bad thing. Okay, and as I said, you know, we're not here to screw you guys. The more effort we see from you, the more help you will get from us. Okay, so if we see that you put in a lot of effort, you put in an honest work, then we will be more generous with how much we'll help. But, you know, if you show up, you know, clearly you haven't even thought about the problem, then we won't be able to help much. And this brings me to the next point, which is that you have to make use of the office hours in this course. It is very crucial that you get help when you need help, and that you're not just like burning tens of hours on a single problem and banging your head. So please make use of the office hours. Okay, and I'll add that, you know, some questions are designed in the homework with this in mind, that we expect you to come to us for hints and help. All right, so keep that in mind. And also, let me make the following point, that, you know, if you look at the grading scheme, 60% of it is like exams, the midterm and the final. Right? And you might ask, well, how do I prepare for these exams? That's the thing that's going to determine my grade. Well, the best way to prepare for the exams is to give an honest effort in every assignment and every homework. Okay, the homeworks prepare you for those exams, and if you do that, then you should be fine for the exams. So the homework system is going to be a bit different this year, okay, this semester. So we're going to have 3 types of questions, first of all. These are going to be solo questions, group questions, and open collaboration questions. So you can sort of guess what these mean. Solo means you work by yourself. These questions are going to be sort of easier usually than the other questions. They're intended to be like warm-up questions in some sense. Then we have group questions, and you have to work in groups of 2 or 3 for these questions. So you're not allowed to work alone, and you're not allowed to work in groups of more than 3. Okay? So why aren't you allowed to work alone? Well, first of all, these questions are difficult. So we're trying to save you from yourself in some sense. If you decide to work alone, you might find that you're in trouble. But the second thing is, like, even if you are able to do these questions alone, it is an important skill to learn how to work with other people. So that's the purpose of these group questions. And then there's a third category, which is called open. And this is like work with anyone you want in class. Okay, so for these, if you want, you can work alone. You can work with the other 190 students in class if you want. So it's up to you who you work with for these ones. But it has to be within the class. Now, there are some general rules that apply to all of these kinds of questions. So let me just quickly say some of these. But all the rules are in the course webpage, as I said, and you have to read these course policies. Okay, but here are some of them very quickly. So don't share written material with anyone. Okay? Any kind of written material. So written on paper, electronically written, whatever. So erase public whiteboard when you're done, so you can discuss your ideas with your friends on the public whiteboard, but please erase it after you're done. You are welcome to search books, read books, and learn general concepts if you would like to. And I mean, it's actually encouraged. And in the same spirit, you are welcome to Google general concepts if you want to learn something. But what is not allowed is you cannot Google specific keywords that appear in a homework question. Okay? And always cite your sources, right? Write down the people that you have worked with. If you use the book or if you read something on Google, cite these sources. For collaborative problems, think about the problem for at least like half an hour before you collaborate, because first of all, it's good for you that you first understand the problem, and it's good for your group members as well, so that when you come to discuss a problem, you already know what the problem is about and what the challenge is. Then you can work on that immediately. Now, one of the main changes that we're going to have this semester is homework writing sessions. So you are not going to, let's say there are, 7 problems on the homework. So you're not going to actually write the solution to these 7 problems and hand them in. Okay? So what's going to happen is that we're going to have homework writing sessions. It's going to be on Wednesdays from 6:30 p.m. to 7:30 p.m. at Doherty Hall 2210. Here we're going to randomly pick a subset of the problems, maybe like 3 problems. And you're going to be asked to write the solutions to those 3 problems during that hour. Okay? Now, this is not an exam. This is not a test, right? This should be a very stress-free, easy session, right? Because the expectation is that you already know the solutions. You have figured out the solutions to the problems. You have already practiced writing those solutions, right? As if you were going to hand in those solutions. So you've already done that. So you know how to write it. So you go in to these homework writing sessions, and you just write the solutions down, and that's it, right? Easy. The hard part is figuring out the solutions, right? I mean, I'm not claiming that's an easy thing to do, but once and that's going to be there regardless. Even if we ask you to hand in the solutions written up solutions, you have to figure out the solutions to those problems. But once you have figured it out, once you have practiced writing these solutions down, then this shouldn't be really a big of a deal. But it is really important that you do write these solutions down beforehand, right? You're not writing the solutions for the first time during that homework writing session. If you do that, you're gonna be in trouble, okay? And also, I like to just point out that the clarity of your solutions is very important. The presentation of your solutions. So also put a lot of effort into how you're presenting. If you're writing a proof, how you're presenting that proof, and that it is very clear. And every step is clear and follows from the previous steps. So we're going to reserve 20% of the credit for presentation. Okay? Quizzes. So quizzes, we're going to have basically a quiz most Tuesdays from 9 a.m. to 9:07 a.m. Okay? So at 9:07, we are picking up the quizzes for sure. Okay? That means that if you want to get the full 7 minutes here, then you need to be in class, be seated in class at 9 a.m. Okay? So you won't get full time if you come to class late on these. Now, the quizzes are not meant to be stressful in any way. They are just a check that you remember the previous week. They're going to be easy, really. Okay? Just a little check that you are following the weeks, and maybe a little incentive for you to come to class at 9 a.m. in the morning. Okay. We are going to use Piazza, so make sure that you are signed up for Piazza. The course announcements are going to be made on Piazza. It is a great resource, so make sure that you make use of it. Ask questions on Piazza. Please be polite. Keep the discussion polite. And also, don't give away any hints about the homework problems there. Office hours. So let me tell you about the office hours for the instructors. Oh, that's Piazza again. Office hours. So Ryan is going to have office hours Tuesdays and Thursdays right after class. Like at 10:30 in 15 minutes, he has actually office hours. Okay, so you can go to him. And I have office hours right after his office hours. Okay, for 1.5 hours. So these are great times. So obviously Tuesdays, we expect you to come with lots of homework questions, and that's fine. But these office hours are great times to ask questions about the lectures, to get clarifications about the lectures right after the lecture, right? So this is all going to be online, so you don't have to write it down, of course. The TAs, for example, see the course webpage. I'm not going to list all the TA office hours, but as I said earlier, and I'll say it again, you have to make use of the office hours in this course. It's very crucial. If you don't, you're really shooting yourself in the foot. So please avoid doing that. Now let me quickly go over a typical week with you. Okay, so today is Tuesday. We have a lecture. Ryan has office hours right after the lecture. I have office hours right after Ryan's. And then it's Wednesday. Well, there's no homework out yet, right? So you're going to be waiting around a little bit. Well, I guess you are taking other courses. I don't know why. Okay, so then the homework writing session. What's going to happen on Wednesday night? We don't have homework. While you're still required to go to this homework writing session because it's going to be a chance for you to meet your TAs, do some fun stuff with the TAs, and also perhaps find some group members for the homework. Finding good group members is very important, right? So, you want to work with people with which you can get along well with, and you have good chemistry with. So Thursday comes, it's a lecture, it's office hours after the lecture, and then the homework comes out. Okay? All right, so then you read every question, of course, when the homework comes out. You have an idea about what's being asked. And then Thursday night, you start working on the solo problems. Very good. These are like warm-up questions for you. And then Friday comes, and Friday is recitation day. So you have your recitation, and then you work on the solo problems. You try to finish the solo problems Friday. And then you start thinking about the group problems as well. And then you also make appointments with your group members to meet over the weekend to do the homework. Okay? Then Saturday comes. You meet with your group. Yeah, that's gonna happen. You make some progress on the questions. Some. Maybe you solve some of them. Who knows? But then it's good because there are actually office hours on Saturday. So you go to office hours and you get the help you need. And then Sunday comes. You think Sunday might be an off day, but of course, you meet with your group, go to office hours, get some help, solve some more problems. And then Monday comes, and then you have also other courses you're taking, of course, I realize. But you have to finish up the group problems, hopefully. And then you have to do a quick review of last week, because Tuesday is quiz day. Right? So you do a little review. And then Tuesday comes. Oh, you realize there are still open problems. Uh-oh, you say, what am I going to do? You express hate towards the professors. And then like Tuesday is like a quiz day, so you have to wake up early and make the 9 a.m. class. And waking up early sucks too. And then you go to the lecture. You rush to the office hours after the lecture. You get the help, try to get some help. And then you don't sleep until you solve the hardest problem. Actually, you should not be doing that. Like, that's the worst thing you can do to yourself, is to not sleep. And then Wednesday comes. So then now you practice writing up the solutions to the problems. You solve the problems, you practice. And then you realize you have a mistake. Right? And then you express it. So the point is here that once you solve a question, once you think you solve a question, you write it down immediately. Because that's a check that you actually have the solution. Because a lot of the time you think you have a solution, but there's a bug in there somewhere, just like a programming bug. Okay, I had some video. I'm going to skip that. All right, so I'll see you guys on Thursday.